theorem, there is a possibility, okay, even if these probabilities are getting smaller and smaller and smaller, but there is a possibility, okay, that this, for some realization, okay, for some realization of the random variables, this event may occur actually. So you can have, the situation where the sample average is different from the actual average by choosing number actually. So there are what you call underlying possibilities that this may occur, okay, but because it can happen actually that even the probability, the events with a very low probability occur actually, okay, even there are extremely low probabilities, but those events occurs, okay. But this theorem guarantees that the sample average must converge to what do you call the population average, okay, with probability 1 actually. So in this case, every realization of this sample average will converge to the population average. Okay, so there is no possibility that the sample average is not converging to the actual average actually, okay, or the population average. While in this situation there are limitations, there are possibilities actually. So that's really the key difference actually between both. So I hope you got some sense of the difference of the both of the results actually. There can be another way to interpret what do you call the strong law of large numbers, and I borrowed this interpretation from Ross. It's a very good interpretation. I liked it, so I thought that I must talk about that with you. So suppose you do you do an experiment in which you perform a lot of independent trials actually. Okay, could be any experiment. Okay, suppose you do an experiment in which you are performing a lot of independent trials. Okay, so for example, one of example could be that you took 2 coins and you are flipping them again and again and again and again and again. Okay, you are flipping them again and again and again. So the experiment can have number of trials, independent trials. Okay, and this is not, so this is just one example of it, but this is more abstract actually. Okay, and in this experiment, okay, say E is the event actually, one fixed event that in which you are interested in actually. Okay, so E is some fixed event that you are interested in. Say you are interested in that 2 times a tail appears. So if you flip 2 coins, so it may or may not happen that the 2 times tail occurs actually. Okay, and happening of this is what you call 1/4. Okay, so we have an experiment consisting of a lot of independent trials, and E is one of the fixed event, okay, in this experiment that may occur on some trial actually. So in other words, on first trial you can get both tails, or on second trial you can get both tails, or third trial you can get both tails. Okay, so this E may occur on any of the trial actually. Okay, now let's Xi, using this E, let's introduce a sequence of random variables. Xi is the indicator function of the event I. I'm going to say that Xi is equal to 1 if E occurs, and is going to be equal to 0 if E does not occur. So I'm defining Xi. Okay, so X1 is what? X1 is what? The event that on first trial E occurs. So X1 will take value 1 if E occurs, and it will take value 0 if E does not occur. And X2 means what? that on second trial E occurs. In other words, on second trial you got tell. Okay, you got tell. And so on and so forth. So what does law of large number is going to tell you? Law of large number is going to tell you that if you take, say for example, average of the first n trial, if you compute the average of the first n trial, this average will converge to the population average. So this sample average will converge to the population average expectation of xi. And expectation of xi is the expectation of indicator function. And we know that the expectation of the indicator function is equal to the probability of E. Okay? Is equal to the probability of E. So this we get from strong law of large number. Now what does really all this stuff mean? What would be x1 plus x2 plus xn? What would be the interpretation of x1 plus x2 plus xn? The interpretation of x1 plus x2 plus xn is that this is the number of times. So you did n trials, okay? So in n trials, sometimes E occurs and sometimes E does not occur. So x1 plus x2 plus up to xn is the number of times that E occurs in first n trials. So this is representing that number. Now this number can be 0, in other words E doesn't occur in first n trials. It could be 1, it could be 2, it could be any number actually. Okay? So this x1 up to xn represents the number of trials that E occurs, number of times E occurs in the first n trials actually. Okay? And what does this statement is telling you? This statement is telling you something, interesting, because this says by a strong law of large number, with the probability 1, number of times that E occurs divided by n, number of times that E occurs divided by n is equal to the probability of the event actually. Is equal to the probability of event. So what do I mean by all that? So imagine you flipped these two coins 100 times. And you treat A as the event, what do you call, when both coins show tell. The strong law of large number tells you that in 100 flips, it is guaranteed that TT, okay, that both tells will show up at least 25 times. 25 times, okay, 25 times. The 1/4 of the 100 times actually. Okay, 1/4 of the 100 times. I mean, you can take this and say, for example, multiply with this, okay, and you're going to get that the number of times E will occur is equal to the probability of E multiplied by n. So what does this shows? What does strong law of large number is suggesting you? That if you do, this flipping of two coins experiment 100 times, it is guaranteed with the probability 1, almost surely, out of these 100 times, 25 times your event will occur. The event that you are interested in, this will occur. For sure. 25 times. And how did I got that 20? So I multiplied the probability with the number of times. In this statement, if I multiply both sides by n, the number of times event will occur is equal to what? N multiplied by the probability of T. So 1/4 multiplied by the 100 actually. Okay. This is another interpretation, a very interesting interpretation of what you call the strong law of large numbers, that you repeat some number of trials, you are repeatedly doing an experiment, Okay, and in that experiment you are interested in an event, and you want to know that how many times this event will occur in, say, first n trials actually. Okay, the number of times that your required event E will occur in, say, first n trials is n multiplied by the probability of that event. N multiplied by the probability of event. So I hope this is making a little bit of sense to you. So I hope I have sufficiently talked about the strong law of large numbers and how a strong law of large numbers is different from weak law of large numbers. What is the difference between both? Why strong law is a strong law and why weak law is why weak law. I'm not getting into more details of almost sure convergence and probability. We're going to cover this, in our major theoretic probability course, our stochastic calculus course actually. Okay. So now I want to, justify what you call the law of large number. Okay. So whenever law of large number comes in your mind, you should always have it had that you have a population with a common mean. The law of large number says that as you increase the sample size, the sample average will converge to the population mean. That's what essentially it says actually. So I hope it is making sense to you. Now, the proof of law of large numbers is pretty much complicated actually. Okay? So if I prove this law of large numbers without giving you, for example, a breakdown of it, that what is going on, otherwise you will be lost in the proof actually, that from where we started and where we are heading and what actually we want to do. Okay, so before writing the proof of the law of large number, I want to give you a breakdown, the steps that we're going to take to prove the law of large numbers, because in each step you will not be lost. You know that where you are heading actually. Okay, so you know that where you are going. Okay, so the strategy to prove the strong law of large numbers, we can prove this without this assumption, but we're going to prove the strong law of large number with the assumption that the fourth moment of the population, the entire population, is k, and it's a finite number. Okay, so we are assuming, so that's a big assumption, the strong law of large number can be proved without this assumption. Okay, but we will prove under the assumption that the fourth moment of the population, entire population, in every single random variable is a finite number. Let's call it k actually. So this is generic assumption actually. First we will prove the special case of the strong law of large numbers, when the expectation of the population mean is 0. Okay, in other words, the mu is 0 actually. So what we will like to prove, we will prove Sn divided by n, average population, where by Sn I mean the sum of the first n observation, and Sn by n is really representing the sample average. So what is actual average? 0, and Sn by n represents the sample average. So we will prove that this sample average will converge to the actual average, which is 0 with probability 1. This is what we will like to prove, that Sn by n converges to 0 with probability 1. How we will prove it? We will actually prove a lemma in which we will prove that the fourth power of the sample average, Sn by n power 4, goes to 0 as the sample size increases, as n gets bigger and bigger with the probability 1. We will prove this, because if this is true, then I can take, what do you call, the fourth root on the both sides of the limit and conclude that Sn by n converge to 0. So in order to show Sn by Sn goes to 0, I will prove that Sn I will prove that the sample average Sn divided by n power 4 goes to 0. And by taking the fourth root, we will deduce this. So if this is true, this must be true as well. And how I'm going to show this actually? So what will be the step that I'm going to use to show this, that this will occur with the probability 1? I'm going to show that if I take this, term as n by n power 4 and make a series out of it actually, okay, and make a series out of it, then this series converges. This series converges with the probability 1. And we know a result from real analysis, okay, so-called sometimes it is also called the divergence test for convergence of series actually. So what does this series, this result tell you? I equal to say n equal to 1 to infinity. If you have a sequence of real numbers, a series of real number that converges, okay. So if you have a series of real number that converges, then this sequence, okay, this sequence an will converge to 0 as n goes to infinity. So if the series is convergent, then its representative sequence goes to 0 as n goes to infinity. So if I'll prove this, then by this result, so if the Sn over n power 4, okay, Sn over n power 4, so this series is convergent, then by this result from real analysis, it will prove that Sn power n power 4 converges to 0 as n goes to infinity. And if Sn power 4, Sn divided by n power 4 converges to 0, then their fourth root, in other words Sn by n, converges to 0, okay, as n gets to infinity. So that would be the proof, and that will prove the strong law of large numbers in the case when the population mean is 0. And then we're going to prove the general case actually, which is going to be really deduction from here. It will be really corollary actually, that if your population mean is non-zero, then you can introduce these random variables actually. So we will talk about it, that how the general case follows from this case actually. Okay, so I hope you got the strategy. So our focus would be to prove this lemma, because if this is true, the strong law of large number is true. But in order to prove this lemma, in order to show that Sn over n power 4 goes to 0, we will show that this series is convergent with the probability 1 actually. Okay, this series is convergent with the probability 1. So I hope this is making sense to you. So that's what we will like. So we like to attack this problem. We'll compute Sn by n power 4 first, and then we'll make a series out of it, and then we'll show that that series converges with probability 1. Okay, so this is what is really the breakdown of the result. So let's just start with the proof of this lemma and say let's get rid of all this stuff. So let's prove this lemma first. That Sn power n power 4 converges to 0. The sample mean power 4 converges to 0 as n goes to infinity with probability 1. Okay. That is probability that limit n goes to infinity, the fourth power of the sample average is equal to 0. This probability is 1 actually. So this is what that we are interested in proving. So here's a proof. So let's start with computing, say, Sn power n power 4. Okay? Let's start with computing Sn power divided by n power 4. Now what is Sn? Or maybe let's first compute, say, Sn power 4 actually, and then we can divide it by n power 4 easily. So Sn power 4 is the sum of the first n observations. Okay? Xn power n. This is what the power 4 actually. Okay? Power 4. Now in this sum, so you have n terms n power 4. Okay? You have n terms n power 4. Let me give you an illustration. So imagine you have a plus b plus c plus d, say, plus e power 4 actually. So yeah, I have 5 terms and 4 powers, for example. Okay? Now when I'll expand it, this expansion consists of the 4 kind of the terms actually. Okay, the 4 kind of the term. The first kind of the term is going to be the terms with the power 4. Terms with the power 4. How many terms are going to be these? So what would be the terms with the power 4? It could be, so here a can come, so one term would be a power 4, other term would be b power 4, okay, the third term is going to be c power 4, okay, and fourth is going to be d power 4, okay, and e is going to be, okay, what do you call, e power, the fifth is going to be e power 4, okay. So there will be a power 4, b power 4, c power 4, d power 4, e power 4, okay. So there will be some terms in which, power 4 come. And you can fill this bracket, you can treat this bracket as, this bracket could be A, could be B. Whenever I write this, like it could be any one of these things actually. C, D, E, could be any one of these. So there will be some terms of like this actually. By the way, how many terms are going to be like this actually? How many terms, if I ask from you that how many terms are there which are of this form, power 4. So these are going to be, so how many these numbers are there actually? So 5. So out of 5, I need to choose one and substitute it here. So there are going to be 5 choose 1 terms of this form. 5 choose 1 terms of this form actually. Okay? What would be the other forms of the terms, for example? The other form of the term could be that I have a term with power 3 and the term with power 1. Okay? The term with the power 3 and the term with the power 1. By the way, these 2 terms should be different. Because if I put a here and a here, so it is included already here. Okay? So these 2 terms should be different. So I can have a B, a C, B D, okay, a D, a E, whatever. So there are going to be the term of the 4 degree, in which these two are different actually. Okay, and how many such terms are going to be there? So it is going to be 5 choose 2. Okay, 5 choose 2. But there are going to be terms. I mean, if you look at the, for example, binomial coefficient. Okay, so if I binomial expansion actually say a plus b power 4. So how many terms are going to be there in which there is a cube and b? You're going to say that okay, these are there are going to be 4 choose 3 such terms actually. In other words, out of 3 brackets, you are choosing A, and from the rest you are choosing B actually. Okay. So first of all, I need to choose first 2 variables. So this 5 choose 2 is for the 2 variables. Okay. And then out of what do you call 4, I need to choose, for example, I choose in here A and choosing here, for example, B. So how did I made this term? Out of 4 brackets, okay, so it's like I can treat this as like, okay, like this bracket is being multiplied 4 times, okay. So out of these 4 brackets, I am choosing, what do you call, out of the 4 such brackets, I am choosing A out of 3 brackets and B out of 1 bracket actually. So in how many ways I can do it? I can do it in 4 choose 2 ways. So this is going to be the total number of the terms of this form. Okay. What could be the other forms? For example, other form could be that okay, I have, it consists of say 2 terms, but with a square degree. Okay, with a square degree actually. Okay, so what is going to be then happen actually? Okay, what is going to then happen? First of all, what numbers can come here? How many choices do I have for these 2 brackets? So I can choose AB, AC, AD. So put A here and D here, or A here and B here, and C here and D here. So I have 5 choose 2 choices actually. And how many are going? Once you choose, for example, A and say E, the question is how many terms are going to be there with A square, E square? So this is same as that out of any 2 brackets you choose A and from rest you choose E actually. So these are going to be 4 choose 2. 4 choose 2 terms. Okay, so let's call this. What would be the other kind of terms that appear in here actually? So the other kind of terms that can appear here are, say, I have a bracket with a square and a bracket and a bracket. So this is also a kind of a term that will appear in this section. In other words, you have a square, B and D actually. Such kind of terms can also exist. Okay. Now, how many terms, such terms are going to be there? So first I have to, out of 5, I have to choose, say, 3 symbols, say A, B, D, and make a such term. And then out of, what do you call, 4, by the way, we don't need